All right, so this is problem number 3 on page 13-6. So go ahead and turn to that. And I want you to do this along with me in your notes and just kind of follow along. But it says we have 3-point charges, then they give us to us Q1, which is 8 microcoulombs. Remember, 8 micro, let me just write this down, micro is 1 times 10 to the negative 6. So micrometers would be 10 to the negative 6 meters. In this case, just microcoulombs. Coulomb is a charge. And the reason that Q1 is positive is because it's lost enough electrons that it gained 8 microcoulombs of charge. Q2 is negative 4 microcoulombs, and Q3 is plus 2 microcoulombs, and they're placed in the corners of an equilateral triangle. So let me go ahead and draw that. Well, go ahead and read this. It says each side is 80 millimeters long, so that means each side is 8 centimeters, which we know in terms of a distance, the length of each side would be 0.08 meters. So let me go ahead and write this. We know the charge down here, that's Q1, which is 8 times 10 to the negative 6 coulombs. Then I move over 80 millimeters, or 0.08 meters, and there's a negative charge, I'm going to say Q2, that is negative 4 times 10 to the negative 6 coulombs. And then right above it, in an equilateral position, there's another charge, Q3. So Q3 is equal to 2 times 10 to the negative 6 coulombs. All right, and it says the base of the triangle is formed by Q1 and Q2, which we already have. Q1 and Q2 is by base of the triangle. What are the magnitude, so size, and direction of the resultant force on this guy, the 8 microcoulomb charge? So I'm interested in finding the resultant on that guy right there. Okay, so all these guys are interacting, but all I care about is what's the force on him. So here's what I'm going to do. I'm going to make green the force that Q2 acts on Q1. So take a look. Q2 is negative. Q1 is positive. So Q2 is going to try to pull Q1 to the right with some force. I'm going to call it F2 due to the fact that it's from charge 2. Okay. Now it just so happens, don't have to worry about writing this down, but I was going to show you. So it just so happens that Q1 pulls Q2 to the left with the exact same force, but we don't care about that. All we care about is what's on the 8 microcoulomb charge. All right, and then Q3 is also interacting with Q1, and I'll do this in blue. So blue is Q3, but because he's positive, he's actually going to push him away along that same line right there. Okay, so I'm going to call that F3. So let me write this down. F3 is Q3 on Q1, and F2 is Q2 on Q1. So if you guys take a look, there's actually 2 forces acting on Q1. All right, he's not going to feel them individually. He's going to feel one big force. Well, how do I add them together? Well, I can't just simply add the forces together because they're vectors. But before I can even think about adding them together in the first place, I need to find out what F2 and F3 are. So let's go ahead and do that really quickly. F2 is going to be K Q1, Q2, because the green is those 2 charges all over the distance between 1 and 2 squared. Now remember, there's absolute value bars right there. All right, so I'll go ahead and plug in. K is 9 times 10 to the 9th newtons times meter squared over coulomb squared. Q1 is 8 times 10 to the negative 6 coulombs times, I don't need to worry about negative sign because the absolute value, so I'll just go ahead and say 4 times 10 to the negative 6 coulombs. And that is all divided by the distance between them. The distance between each of the charges in this particular case is 0.08 meters, and that is squared. All right, and so when I punch all that into my calculator, I get 45. Now, what are my units? Well, I'm expecting to get force, so it should be 45 newtons. Well, let's take a look. Meters squared and meters squared will cancel, and coulomb squared and coulomb times a coulomb squared, those will cancel, and so I'm just left with a newton. That is F2. Now, that's the magnitude of F2. Remember, the formula is just going to give me magnitude. We talked about that the other day. How do I determine the direction? I look at the picture. Literally look at the picture. F2 is going to the right, so that I know that is to the right. All right, now we got to solve for F3. So let me switch to blue. So F3 now, remember, is between Q3 and Q1, so that is K, and it's between Q1 and Q3. Doesn't matter the order, right? You're just going to multiply them, and then that's R13 squared. And I'm only using 13 there and 12 there, just so that I know the distance. It just so happens in this particular case that the distances between all the charge, because it's an equilateral triangle, are all the same. So I'm going to plug in. That's 9 times 10 to the 9th newtons times meter squared over coulomb squared times Q1, which is 8 times 10 to the negative 6 coulombs, times, I go back up, Q3 is 2 times 10 to the negative 6, so 2 times 10 to the negative 6 coulombs. And once again, they're both positive, so it doesn't matter, but I don't have to worry about a sign because it's absolute value anyways. And then the distance between them is still 0.08 meters, and then that is squared. And so when I punch that in a calculator, I get 22.5 newtons. Now, if you take a look, all right, if I drew that, if I was to draw an FBD, so let me go ahead and do that, FBD. If I was to draw an FBD, we see that, I'm going to do this like this first. So we see that this is, remember, it's on Q1. Here is my coordinate system. F2 is exactly to the right, and then F3 is down at some angle. Now, what is that angle? Well, this is an equilateral triangle. What do we know about equilateral triangles? Oh, the angles. So that angle right there is 60 degrees because it's equilateral. That angle and that angle are opposite. So F3 is 60 degrees below the negative x-axis. And so this angle right here is 60 degrees. So what I'm going to do is I'm going to go ahead and write that down, that this is 22.5. That's my magnitude. And then the direction is at 60 degrees south of the west line. Okay? And so F2 is this guy, excuse me, F3 is that guy. All right? And so those are the two forces. Now, I can't just say 22.5 plus 45. First of all, this is kind of cool. Everything is the exact same except for that's 2 and that's 4. 2 is half of 4, so you'd expect the force is half because the distances are the same. All right? What I need to do is I need to break this guy up into components. So let's look at that guy a little bit bigger. So I'm going to make him a little bit bigger. How do I break that into components? Well, what I can do is I can think about the x part of F3. So this is F3 in the x direction. And then think of the y part. That's F3 in the y direction. You see that this one is adjacent and this one is opposite. Remember when we break up components, adjacent we like to think of cosine and opposite we like to think of sine. All right, so what I need to do is I need to find that side right there. This is going to be F3 times cosine of 60 degrees. And then that side right there is going to be F3 times sine of 60 degrees. And that's the same thing as saying that right there, but I don't need that. All right, so let me make that smaller again. We'll come back over here. Okay, and so I'm going to say F3 in the x direction horizontal is 22.5 newtons cosine of 60 degrees. And where did I get 60? Just by looking at the picture. All right, and so 22.5 cosine of 60, I get 11.25, so 11.25 newtons. And then which way does it point? Let's take a look. Oh, it's pointing left, so I'll just put a little arrow left. All right, and then F3 in the y is equal to 22.5 newtons sine of 60 degrees. So if I do that real quick, 22.5 sine of 60, I get 19.5. I'll just round to 19.5. So 19.5 newtons. And which way does it point in the y direction? It points down. So it's F3 and the y. All right, so take a look. Instead of having two forces, F2 and F3, we can actually think of this guy feeling F2 that way, feeling F3 in the x direction and F3 in the y direction. So he's getting kind of pulled to the right, pushed to the left, and pushed down. So here's how I got to add vectors. Take a look. This guy and this guy both are in the x direction. So there's x. This guy is the only one in the y direction. So what I'm going to do is I'm going to say, all right, F in the x direction is equal to F3 in the x direction plus F2. All right. When I want to find up I'm going to sum up all the forces in the x direction. Then I'm going to sum up all the forces in the y direction, and I notice that the only force in the y direction is just F3 in the y direction. All right. So I'm going to just keep this all in black now, but F3x points left. How do I plug in left in my calculator? Well, let's call to the right positive, and let's call down positive. You know, whatever we want to call it, that's fine. Right, positive, down, positive. So if that's the case, when I solve for the sum of the force in the x direction, the total, do that in black, the total in the x direction, so Fx is going to be F2, which was 45 newtons, and that's positive because it points to the right, plus a negative 11.25 newtons because that points left. So 45 minus 11.25, I get 33.75 newtons, and because it's positive, it points to the right. So F2 dominates F3 in the x direction. Then Fy is simply just F3y, which is 19.5 newtons, and that's down. All right, and so let me redraw my picture. So now I have an x part that points to the right of 33.75 newtons. So the Q1 is getting pushed or pulled to the right by 33.75 newtons, and at the same time down at 19.5 newtons. Well, how do I add vectors that are perpendicular to each other? Oh, that's easy. I Pythag them. This is the resultant vector. So this is F. That's the resultant vector. I'll say F sub r. I'll write that resultant. Resultant. So Fr is the x part, 33.75 newtons squared plus 19.5 newtons squared square rooted. And if I do that real quick, 33.75 squared plus 19.5 squared, enter. I get 1519, but then I'm going to square root that. And I get 38.97, so I'll just say 39. 39 newtons is my resultant. So that is the magnitude. This is the size. This is the size of push / pull. That's how hard, right? But then I got to determine a direction. We'll take a look. Let's determine that direction. All right, and so how do I find that angle? Well, I can always use the inverse tan function. Remember, inverse tan of the opposite over the adjacent. That's what inverse tan does, or tan does. And so if I do the inverse tan, the opposite was 19.5 newtons all over 33.75 newtons. Newtons cancels. And then I could plug that in my calculator. So inverse tan of 19.5 divided by 33.75. And I get an answer of 30 degrees. Now take a look. That is 30 degrees below the x-axis. So really, I could say south of east. I could say 30 degrees negative, because if I say negative with nothing there, I'm assuming you're starting on the positive x-axis and moving clockwise or counterclockwise. In this case, the negative sign tells me to move clockwise. And the other thing too is the other angle that I could find is technically starting there and going all the way to that spot. And so you know an entire angle is 360 degrees. I'm 30 degrees short, and so I'm 330 degrees also. Any of those work. Boom, boom, or boom. So if I go back up to my original problem, that's up here, the answer is 39 newtons at 330 degrees. So that's what we got. If you take a look, there's my magnitude. That's right there. There's my magnitude. Bam, right there. And then my angle is 30 degrees south of east, or negative 30 degrees, or 330 degrees. So in vector notation, the resultant force in vector notation is 39 newtons. That's the magnitude at 30 degrees south of east. And that's my final answer. So make sure you guys check that out. If you need to watch this again, that's fine. If you need to pause it, slow it down, all that kind of stuff, that's great. But make sure you guys look at this, because this is going to be helpful for some of the stuff that we're going to be doing in this particular unit.